Hello students, welcome to second lecture of S block elements. So in today's lecture we are going to start with physical properties of S block elements. So all the alkali metals are silvery, white, soft and lightweight metals. Because of their large sizes, these elements have lower density which increases down the group from lithium to cesium. That means, as we discussed earlier, they are the first member of their periods, respective periods. So that means their sizes will be largest from the remaining elements of the same period. And it also represents larger size with less mass, because as we move from left to right in periodic table, we discussed that their radiuses are shrinking, but at the same time their masses are also increasing. That means as you move from left to right in periodic table, masses are increasing and volumes are decreasing. That represents increase in density. So that means initial elements will have lower density, so it is mentioned. And as we move from top to down, all the number of electron, protons and neutrons are increasing at the same time. That means masses are drastically increases, and that's why as we move from top to bottom, lithium to cesium, densities increases. However, potassium is lighter than the sodium. The melting and boiling points of the alkali metals are low, indicating weak metallic bonds due to the presence of only a single valence electrons in them. Now, metallic bond, as we discussed in type of the bond, when we have two different type of metal atoms, when they combines with each other, they forms metallic bond. Now let's take an example of sodium to understand the nature of metallic bond. Suppose this is the sodium atom, and its outermost orbital contains only one electron, because electronic configuration of sodium is 1s2, 2s2, 2p, 6, 3s1. So outermost orbit contains only one electron. So this unpaired electron is trying to pair up with other electron. So if it is able to pair with other electron, then you will get a pair of electron. But in metallic bond, pair won't occur, but electrons are continuously trying to pair. So two different atoms of the metal will try to combine with each other using that single electron. So because of attraction of these single electrons, these metal atoms will held together in a metallic bond. And in this metallic bond, both of these electrons will revolve around these two nucleuses at the same time. That means they can move around the both of these in this manner. Okay, so we have these two weakly attracted electron towards the nucleus. That's why they are called delocalized electron. They are not localized towards a single nucleus. So let's say, suppose you have five of them, five different atoms, and each contains one electron as a valence electron. So combinedly, all of these five electrons will revolve around these five nucleus, and because of this, these five atoms are held together, which is known as metallic bond. So higher the number of these type of valence electron, more stronger will be bond and stronger metal will occur. But because of only one electron in all of the alkali metals in their outermost s orbital, they are weakly attracted towards each other, and that's why we have soft metals. The alkali metals and their salts imparts characteristic colors to oxidizing flame. This is because of the heat from the flame exits the outermost orbital electron to a higher energy level. When the excited electron comes back to the ground state, there is an emission of the radiation in the visible region of the spectrum as given below. So here few metals are mentioned: lithium, sodium, potassium, rubidium and cesium, and all of them emits colors, or they give specific colored flames when we expose them in oxidizing flame. So it is a simple procedure. First, atoms will absorb the energy, and with the absorbance of energy, electrons present in outermost orbitals will jump to the higher orbital, and when they come back, they will emit the energy. So that means electron needs energy to jump from lower energy orbital to higher energy orbital, but eventually they will come back in ground state, and that means they have to release the energy. So they will absorb the energy in form of heat, and it will remove the energy in form of light. So as mentioned here, lithium will give us crimson red light, sodium yellow, potassium violet, rubidium red violet, and cesium blue. So all of these metals has different orbitals. That's why they give different type of colors, and this property is actually useful in practical. So during the practical, if a given metal is unknown or given salt contains unknown metal or positive ion, then we can do oxidizing flame test. So in flame test, when we put a small amount of this metal on the oxidizing flame, then flame will give one of this color if one of this metal is present. That means, let's say our sample contains sodium. So when we burn sodium in oxidizing flame, flame color will change to yellow. Similarly, if we have potassium, then flame color will change to violet. So alkali metals can therefore be detected by the respective flame test and can be determined by flame photometry or atomic adsorption spectroscopy. So flame photometry, it uses the same principle. From the color of flame we can identify unknown sample, and atomic adsorption spectroscopy, it is already discussed in structure of atom unit. In structure of atom unit, we discovered that when we impart white light on the substances, they will absorb some of the radiation or some of the wavelengths from it. Now all of the white light, actually it is made up of different type of wavelengths, normally red to blue or violet. So when we pass the light after the absorption from the prism, then all of these wavelengths will spread out, or all of the colors will spread out, and we can check which of the lights or wavelengths are absorbed. And when those excited substance, after the adsorption of energy, substance will get excited. So that excited substance eventually will release the energy in form of light. So it will produce light, and we can again pass the produced light from the prism, and all of that light which was absorbed earlier will come as a result. So it is called adsorption spectra and emission spectra. So same type of practical is mentioned here. So when these elements are when irradiated with light, the light energy absorbed may be sufficient to make an atom lose electron. So this property makes cesium and potassium useful as electrodes in photoelectric cells. Now all the properties of this type of metals are mentioned in this table. So physical properties of alkali metals, we have multiple different type of data mentioned here. So as per our requirement, we will discuss it from this table. But let's take a quick overlook. So first is atomic number, we already discussed about it. Second one will be atomic mass. Then electronic configuration, we know the basic electronic configuration of these metals. Then we have ionization enthalpies. That means to produce ion from these given metals. So as we can see, initial metals, because of smaller size, their ionization enthalpies are larger. And as we move from top to bottom, these energy values are decreasing. That means removal of electron becomes easier because of larger size. Now for francium, we do not have enough data because of its radioactive nature and very short lifespan. That's why its value is mentioned as approx. And you will notice many values are not even mentioned because we do not have enough data. Then we have hydration enthalpy. So again, we already discussed about the hydration enthalpy. Then we have metallic radius. That means radius in their atomic state. You will notice atomic state radiuses or metallic radiuses are larger than their ionic radiuses, because when this metal produces ions, they are actually losing the electrons, and by the losing electron, orbitals will shrink, and that's why radiuses also shrinks. So all the metallic radiuses are larger than their respective ionic radiuses. So if negative ion is there, then opposite will be there. That means atomic radiuses will be smaller than ionic radiuses. Negative ion normally accepts the electrons. So as we add the electron inside the orbitals will expand, and that's why sizes will increase. Then we have melting points, boiling points, density related discussion was already done. Then standard potentials. Standard potentials are, it can be represented as a tendency to reduce itself. If element feels stronger attraction towards the electron, then normally that element will reduce. So if tendency of reduction is stronger, then standard potential will be higher. And if tendency of reduction is lower for self reduction, then it will be comparatively lower. So as we can see, all of these metals shows negative value of standard potentials. It represents their normal nature is to get oxidized. It will lose the electron. Reduction, that means acceptance of electron. Oxidation, that means removal of electron. So all of them shows negative value. It represents they are highly electropositive. Normally they will lose the electron. And next occurrence in the lithosphere. So all of them are mentioned as per their quantities in the lithosphere, that means upper part of the earth. Now let's talk about the chemical properties. The alkali metals are highly reactive due to their large size and low ionization enthalpies. The reactivity of this metal increases down to the group because as we move from top to bottom, sizes are increasing, and that's why the reactivities are increasing. So first, reactivity towards the air. Alkali metal tarnish in dry air due to the formation of their oxides, which in turn react with the moisture to form hydroxides. They burn vigorously in oxygen forming oxides. Lithium forms monoxide, sodium forms peroxide, and other metal forms superoxide. The superoxide O2 minus ion is stable only in the presence of large cations such as K, Rb, and Cs. Now simple explanation of these type of differences, that means for smaller ions we have monoxide, for medium sized ion we have peroxides, and for comparatively larger sized ion as mentioned here you can get superoxides. So simple reason, in this case all of the metals are positive in charge, for example lithium, and as discussed earlier, lithium forms positive ion by losing the electron, and because of losing the electron its size is even smaller. It is already a small atom, and when it loses electron it even gets smaller sized ion. On the other hand, we have oxygen in negative form. That means oxygen will accept electrons, and by accepting electron its size will increase. And normally as you can see in this case oxygen is in -2 oxidation state. So it is accepting 2 electrons. So its size will be comparatively very large. So that means oxygen is comparatively very large. So we cannot attach two oxygen at the same time with a small sized lithium because it is very small, so simply it cannot reach to the both of these oxygens, and that's why smaller sized atoms are not able to attach with comparatively more number of oxygens. And all of these reactions are mentioned for lithium. As we can see, 4 lithium with 1 oxygen molecule gets Li2O oxide. Then sodium forms peroxide, and metals like potassium, rubidium, cesium forms superoxide. In all the oxides, the oxidation state of the alkali metal is +1. Lithium shows exceptional behavior in the reacting directly with the nitrogen of the air to form the nitride, Li3N as well. Because of their high reactivity towards the air and water, alkali metals are normally kept in kerosene oil. So that means if we place sodium metal in open atmosphere, it will react vigorously. It will blast itself by reacting with the moisture present in air. Similar situation with potassium. Potassium will react even more vigorously. So that's why we have to keep all of these metals in kerosene oil. Next, reactivity towards the water. Alkali metal reacts with water to form hydroxides and dihydrogen. So this type of reaction can be used for the production of the H2. But this is vigorous reaction, so we should be careful. In this reaction, energy will be produced. This is exothermic reaction, so heat will evolve during this process, and at the same time hydrogen gas is also being produced. So produced heat will ignite the hydrogen and you will notice a blast. So that's why these reactions are quite dangerous. So it may be noted that although lithium has most negative E naught value, its reaction will be with water is less vigorous than the sodium, which has least negative E naught value among the alkali metals. This behavior of lithium is attributed to its small size and very high hydration energy. Other metals of group reacts explosively with water. And they also react with proton donors such as alcohol, gaseous ammonia, and alkynes. Next, reactivity towards the dihydrogen. The alkali metal reacts with dihydrogen at about 673 Kelvin, lithium about 1073 Kelvin. To form hydrides, all the alkali metal hydrides are ionic solids with high melting points. So metal plus hydrogen produces metal hydrides. As we know, hydrogens are electropositive, but they are less electropositive than these metals. So these metals are highly electropositive, so high that even they can get negative hydrogens. So with these type of strong electropositive metals, hydrogen will form hydrides, that means negative hydrogen. Next, reactivity towards the halogens. Now these alkali metals and halogens, they are exactly opposite nature from each other. All of the alkali metals are strong electropositive metals and all of the halogens are strong electronegative elements. So the alkali metals readily reacts vigorously with the halogen to form ionic halides M plus X minus. However, lithium halides are somewhat covalent. It is because of the high polarization capacity of lithium ion. So high polarization capability, that means the distortion of electron cloud of the anion by the cation is called polarization. That means it is induced dipole like situation. First of all, how bond nature is decided. That means whether bond is covalent or ionic. So simple thing is it depends on the electron distribution. Suppose we have two different type of elements A and B, and this is their bond. So this is the center of bond. One electron is shared by A and second electron is shared by B. Let's represent electron of A with dot and electron of B with X. So if this electron pair is present exactly at the center, then this bond is covalent bond. As we move this electron pair towards the one of these two element, let's say B is more electronegative than A. So this electron pair will be present comparatively closer to B and away from the A. Then this bond is still covalent, but it is polar covalent bond like water. And as we move this electron pair towards the B more and more, that means we are decreasing the distance from B and increasing from A. So now let's say our electron pair is here. So this bond will become more polar, and polarity actually represents ionic character. As we know, polar bonds are represented with partial negative and partial positive charges. In case of iron, these partial positive and negative charges are strong. So let's say this electron pair shift even more closer to B, then now it falls into the category of ionic bond. So in ionic bond, more than 50% character is ionic character and less than 50% character is covalent character. Okay, so that means in any bond, if more than 50% covalent nature exists, then we represent that bond as covalent bond. And if more than 50% nature is ionic nature, then we will represent that bond as ionic bond. So that means all type of bonds contains both type of nature, more or less, but both type of nature. So we are calling them by the more dominant nature. If ionic nature is dominant, then they are called ionic bonds. If covalent character is there or covalent nature is dominant, then we will call it covalent bonds. So smaller size of lithium actually increases electrons strongly because it has very small distance from the outermost orbitals. So because of smaller size, it will distort the cloud of negative ion. That means let's say we have chlorine in negative state here. So because of smaller size, electrons of chlorines will feel attraction towards the lithium, and that's why their structure will distort something like this. Electrons will move slightly towards the lithium side, and that's how it gets distorted. And because of this, between them electron pair will shift slightly towards the center, and it falls into 50%, more than 50% covalent nature. Lithium ion is very small in size and has high tendency to distort electron cloud around the negative halide ions. Since anion with large size can be easily distorted, among the halides, lithium iodide is the most covalent in nature. Next, reducing nature. Alkali metals are strong reducing agent. Simple reason, because they have very electropositive nature, so they have tendency to lose electrons. So if they are losing electrons, someone must accept it, and that's why they are strong reducing agents. Lithium being the most and sodium the least powerful, the standard electrode potentials, which measures the reducing power, represents the overall changes. So simple reaction, metal first sublimates from solid to gaseous state. So in this reaction, energy is represented as sublimation energy or enthalpy. Second, metal will ionize, so it is ionization enthalpy. Now ion of metal will react with water and it will produce aqueous solution of respective ion. It is called hydration reaction. So enthalpy of reaction is known as hydration enthalpy. With the small size of ion, lithium has the highest hydration enthalpy, which accounts for its high electronegative E0 value and its high reducing power. And the last one is solution in liquid ammonia. The alkali metal dissolves in liquid ammonia, giving deep blue solution which are conducting in nature. So metal plus NH3, it gives MNH3X plus ENH3Y. The blue color of solution is due to the ammoniated electron, which absorbs the energy in visible light region of the light and thus impart blue color to the solution. So as we can see in the product, we have this compound which is represented as the ammoniated electron. That means electron with ammonia. So this compound is common for all of the alkali metals, and color is because of this compound, not because of the metal compound actual. So because of this compound which is produced by each and every alkali metals, all of them gives same color. The solutions are paramagnetic and on the standing slowly liberate hydrogen, resulting in the formation of amide. So metal ammoniated with electron with ammonia, it gives MnH2 and half moles of H2 when Am denotes solution in ammonia. So if water is present, then it will be aqueous solution. Here we have ammonia as a solvent, that's why Am is mentioned. In concentrated solution, the blue color changes to bronze color and becomes diamagnetic. Now paramagnetic substances feels attraction towards the external magnetic field, and diamagnetic substances feels repulsion, and both attraction and repulsions are weak. And in next lecture we will discuss about the uses